Cool. So welcome back. So we're going to get started. This is just talking, so you can take a nice nap after eating your lunch. And then starting with the next talk after this, we'll start doing the interactive stuff, actually running simulations and so on. So this whole afternoon session is going to be about FireSim. So FireSim is our platform for doing FPGA accelerated simulations using cloud FPGAs and now local FPGAs too. So this makes it very easy to run fast simulations and scale between having maybe one FPGA locally and hundreds of FPGAs on the cloud before, say, an ISCA deadline. So what is the purpose of FireSim? Well, to answer that question, we want to understand more broadly what the architect and chip developers' design flow is, right? And different architects and different chip developers, and whether you're in academia or industry, kind of impacts how importantly or how important you consider these different factors to be. So the first off is high-level simulation, right? So we start out with an idea, we do some high-level simulation, we might write a Python script to kind of understand the design space. Then usually we'll write some RTL and write some software and plug it into some ecosystem. Hopefully at the end of today, your favorite ecosystem will be Chipyard. Then we do some co-design and software RTL simulation, right? So this is what Jerry had you run this morning, which is you're using Verilator or VCS or Xcelium, something like that, to run micro benchmarks on your design. For a long time, number 4 was missing from any open source flow, and that is the ability to do co-design in FPGA accelerated simulation. And note that this is simulation and not prototyping, and we'll talk about what the difference is in the next few slides. But here, what we essentially want to do is take our design and accurately model it on an FPGA and boot an entire operating system, run in interesting workloads, and capture performance measurements. And then, of course, depending on what your interests are, as Vignesh told you about earlier today, you might want to tape it out, get a chip back, or at the very least, get some QR feedback about your design from the ECAD backend tools. But at this point, once you do this, you have lost most of your ability for co-design once you actually get the chip back. So again, FireSim is going to plug into number 4 here, and it's going to let us do co-design using FPGA accelerated simulation. So what about FPGA prototyping? So FPGA prototyping is basically what you do in your undergrad digital design class, right? You take some RTL, you drop it down on an FPGA. So there's an important distinction between FPGA prototyping and actually running FPGA accelerated simulations. And to kind of make that clear, let's take a look at this example where we have some RTL design. Let's say we're going to tape it out. So this is a real ASIC that we're going to build containing a RISC-V SoC, or it is a RISC-V SoC. And let's say we tape it out, it's going to run at like a gigahertz, right? And that thing is going to talk to some real world DRAM. For the sake of argument, let's say it has 100 nanoseconds of latency, right? So if you run software on this SoC, once you get it back from the fab for real, your software is going to see 100 cycles of DRAM latency, right? But if you build an FPGA prototype using the same RTL, it's obviously going to run much slower on the FPGA, right? Let's say 100 megahertz. But that FPGA is still attached to the same physical DRAM with, let's say, 100 nanoseconds of latency. So now if you run software on this thing, right, you're going to see 10 cycles of DRAM latency. So your memory system performance is off by a factor of 10, which is pretty bad. So why is this happening? Well, it's because there are several difficulties with FPGA prototypes, right? In an FPGA prototype, every FPGA clock is tied to a clock cycle of the simulated target, right? So FPGA clock cycle advancing means your target cycles are advancing too. And essentially, the performance of your FPGA attached resources gets exposed to your design, right? And this is partially what's causing that mismatch I showed you on the previous slide. So these two things together lead to a couple of problems. So first, you're going to get incorrect performance modeling, right? The FPGA resources you're attaching to, relatively speaking, don't model correct performance if your goal is eventually to tape out a design. Of course, none of this applies if your eventual deployment platform is an FPGA, then you should just drop it on the FPGA and build it for real, of course. But if your goal is ultimately an ASIC design that's going to run much faster than the FPGA, then you need to correct this somehow. Of course, your simulations are going to become non-deterministic if you're running in an FPGA prototype because all of these IOs are exposed to the real world, right? It depends on the SD card you plug in. It depends on what's on the other side of this Ethernet cable, what DRAM part you have plugged in here. All of those things impact your simulation. And most likely, when you move across different host FPGAs, you're going to get different simulation results. So what we really want then instead is hardware simulators that give us a bunch of nice features. So we want, of course, to be as close to silicon performance as possible. We want them to be as detailed as silicon, ideally just derived from the RTL that we would go and tape out. And we want to have a lot of the benefits that software-based simulators have, right? The ability, for example, to print stuff is something you don't really get out of a regular FPGA prototype, but you can get in FireSim. And we want them to be low cost. So there are expensive platforms you can get from industry that are custom built to do this sort of stuff, but they don't satisfy this low cost goal, right? So our thesis here is that FPGAs are really the only viable basis technology for doing this. And so we're going to build FPGA accelerated simulators with this software-like flexibility using an open source tool, and that tool is FireSim. Of course, you might ask the question, well, why is this happening now? Well, the answer is that a couple of years ago, a bunch of nice trends appeared sort of in our architects stack. Right? The very first one of these was having FPGAs in the cloud, and we'll use them today. We have a lot of nice benefits from using FPGAs in the cloud. Of course, it's not always affordable to run everything in the cloud, so FireSim supports local FPGAs too. But this was really the impetus for getting a lot of this infrastructure up and running. Then, of course, we need some way to take a design and transform it into an FPGA-based simulator. And so having designs expressed in these high productivity hardware design languages makes it very easy to transform designs into simulators. And we'll talk a little bit later about what exactly that means. Then, of course, you actually need something to simulate. None of this is any good if we don't have good processors, good IP to model. And you heard a lot about this this morning in the Chipyard talks. But now we have this proliferation of this open silicon proven hardware and SoCs in particular that we can actually model. And of course, those are no good if they don't have software that's compatible with them, right? And so RISC-V meant that we could get all of this nice software to run on top of the systems that we're modeling. So at a very high level, what is FireSim going to do? It's going to produce these fast, automatic, and deterministic FPGA accelerated hardware simulators that let you do two things, right? You can do pre-silicon verification, understanding whether your design works or not, and performance validation to make sure it's performing as expected. It's going to ingest a couple of things. So your RTL design in some form, the designs we'll talk about today are all Fertile that we get produced by Chisel. But you can also integrate things like black box Verilog, and there are other flows for example, converting Verilog into Fertile that are less well tested. The key downside to this black box Verilog approach is that you get all of the performance modeling capabilities of FireSim, but you won't get a lot of the nice debugging features that we'll talk about later on. Then we tack on a bunch of hardware or software I/O models, depending on what you're modeling. So this is what's giving you that complete closed-off simulation world that's accurately modeling performance around your design. And then workload descriptions. You'll hear about a tool called FireMarshal in a little bit that makes it very easy to get reproducible workload builds for complex software stacks running on Linux with a bunch of dependencies and so on. So in the end, after ingesting all of this stuff, it's going to produce this fast cycle exact simulation of your design and the world around it. And we put in tons of work to make this easy to use. And so we can automatically deploy this onto cloud FPGAs. So today you'll run a bunch of commands. And as I alluded to at the very intro talk of this tutorial, hopefully all of that magic will happen automatically behind the scenes. And you don't even really have to know that there's an FPGA instance somewhere running your simulations. Recently, we've added local FPGA support, and we basically reused all of this infrastructure that we used for deploying cloud simulations and reworked it so a lot of it works basically exactly the same way for a local system. So you can build a local cluster, or you can just have an FPGA attached to your own machine, and you run the same exact commands you would run for a big 200 FPGA cloud simulation, but you just change a few configuration parameters and then rerun the same stuff. Okay, so overall, what are the three distinguishing features of FireSim? So again, as we said, we're not building FPGA prototypes, we're building FPGA accelerated simulators. We're going to automatically build them from RTL designs into simulators. And we're going to get a bunch of nice debugging, resource optimization, and profiling capabilities as a result. As I mentioned on the previous slide, we can now scale from a few on-prem FPGAs to a large number of cloud FPGAs. And having these standardized host platforms also makes it very easy to collaborate with other researchers. So just as we're showing you all today how to run this stuff that traditionally would require you to go buy your own server, attach an FPGA, and try it out, we can do this very easily by sharing things on the cloud, as well as now sort of publishing standardized host platforms for local FPGA systems. And as I mentioned, there's tons of automation in here to hide all that FPGA complexity. And finally, of course, none of this is useful if you can't find it. So it's all open source. and anyone can use all the stuff we're talking about today. Okay, so before we dive into some technical details inside of FireSim, we got to get some terminology straight. So first off, we want to understand the distinction between the target system and the host system. So the target is the machine that we're going to simulate. It's the thing we're actually interested in improving, probably. Then there's the host system. That's just what's running the simulation, right? So the target design in our previous example is that RISC-V SoC that we wanted to tape out. And we would like a closed simulation world around that design. Our host system can be something like an FPGA fabric that's attached to some physical DRAM, but it could just as well be a regular multiprocessor like the software simulations you ran this morning. So FireSim will generate FPGA hosted simulators, just like something like Verilator would generate multiprocessor hosted simulators. All right, so how is this actually going to work? The kind of core principle here is called host decoupling. So we're going to transform our target design into a latency insensitive model using a fertile transform. At very high level, you can think of this as just taking the design and clock gating, right? So we can control each cycle and how it advances on the FPGA, and we can stop the progression of the design if we need to. Then we're going to tack on models for various IOs where we don't really trust that the FPGA IO is an accurate model of the system. And so, for example, we have this phase timing model. There's a whole paper about it. You can find the link in the slides. This is a synthesizable timing model that sits in between your design running on the FPGA and the physical DRAM attached to the FPGA and presents correct timing to your system. And we'll see how that maps down in a second. But we connect those things together with what we call token queues. Essentially, these queues just contain a token in each direction for every cycle, and that keeps your design and the model in sync with each other. So they only progress when both of them are ready to advance a cycle. So then we can map this onto an FPGA. You see the FPGA fabric. You see some physical DRAM attached to the FPGA fabric. We're going to allocate host resources to various models. So again, this timing model is synthesizable RTL that's sitting on the FPGA. And then we have our transformed RTL design sitting here with those queues I just talked about. So now you can see that when you're running software on your RTL design here, when it makes, for example, a memory request, that request goes through this queue, first hits the timing model. The timing model will go access whatever data that request is supposed to, let's say it's a read, respond with. But the result is not released to your system until the appropriate amount of time has passed per whatever timing model you're using. And this timing model has a bunch of both compile time and runtime configurable parameters. You can model different kinds of scheduling policies and so on. But as a result of doing all of this, now stuff running on your SoC sees realistic DRAM latency. And you can imagine extending this to all sorts of other IOs. All right, so what are the benefits of doing this host decoupling? You saw one on the previous slide, but now simulations will basically execute deterministically, right? We have no open world, external world stuff exposed into the simulator. We'll get identical results on different hosts, again, because this closed world is constructed in RTL before it goes through any tool like Vivado and gets mapped onto the FPGA. And we'll get support for a bunch of nice things. A lot of these we unfortunately won't have time to talk about today, but I think most of them we will talk about today. And there are some links to papers for each one as we go. So the first one is software co-simulation. So this is, for example, devices where we maybe don't care so much about performance, or we have a timing model that's sitting on the host system written in software. So we can have software models that talk to stuff running on the FPGA. And you'll use stuff like this implicitly, like the block device, or a more complicated model that does care about performance, like our network models. And that network model, for example, can be used to simulate large targets over distributed hosts. So this was basically the original purpose of FireSim, and I'll talk about this in more detail in a few slides. But this was basically to model a data center mapped onto hundreds of cloud FPGAs. We can also add a bunch of debugging and instrumentation tools. So we had an ASPLOS paper a couple of years ago that added this sort of stuff into FireSim. And Vignesh has another one coming up at this ASPLOS that covers similar stuff, basically adding nice debugging features into FPGA simulators. And then, of course, we can do resource optimization. So because we control how time advances on the FPGA, we can make trade-offs between simulation performance and the amount of stuff we can pack on the FPGA. So think like time multiplexing expensive units on the FPGA. Okay, so what kinds of stuff can you do with FireSim? So there are a bunch of different use cases. The first kind of most obvious one is just evaluating an SoC, right? That's what we'll do most of today, right? Let's say we have some kind of classical performance measurement kind of problem, right? We made some modifications to the core microarchitecture, and we want to evaluate it on spec. So previously, this was actually pretty challenging to run in academia using full reference inputs, right? It would take a long time on one FPGA to evaluate a design. With FireSim, we can fairly trivially map this out to 10 parallel FPGAs on the cloud and run with full reference inputs on something like Rocket Chip in parallel. And the original phase paper used Spec 2017 as its benchmark suite as a result. There's tons of other sorts of design space exploration you can do. If you learn more about Chisel, you'll find out that Chisel has a very nice way of mapping parameters and exploring design spaces that way. And we can rapidly generate a lot of different designs using Chisel. And so FireSim's cloud automation lets us very quickly also spin up jobs to build all of those designs, as well as run all of those simulations in parallel really quickly. More evaluation of SoC designs. This is mostly just work that's used FireSim, lots of security stuff, tons and tons of different accelerators. And another interesting use case is debugging designs. And we'll talk about this in an entire talk later on, so I'll kind of go fast here. But there are a bunch of debugging features in FireSim. Things like assertions actually fire on the FPGA. Printfs actually show up coming off of the FPGA. You can very easily insert ILAs by just annotating some signals. And so what you see on the right-hand side is the FireSim debugging documentation. And again, this is just an index. Each of these links to a page about some debugging feature. And lastly, I'll talk very quickly about profiling designs using this sort of same methodology. So a nice thing we can do, because we control how the hardware design advances on the FPGA, is we can also collect very high fidelity performance profiling information. So traditionally, if you run something like perf on your real system and you increase the sampling rate a lot to a very high number, right, you start perturbing the software that's actually running on your system, right? Because now your CPU is spending time running perf instead to do the sampling. But what we can do, because we control how the clock advances on the design on the FPGA, is just capture full fidelity traces coming out of the system and just pause the simulated system when we don't have enough resources to kind of catch up writing the trace to disk or something like that. And so that means that we can then take that trace and do things like unwinding to automatically construct something like a flame graph that covers all of the software running on the system, right? It includes all the drivers, all the Linux, and more recently, user space support. So we can basically profile a system without really understanding anything about what it's doing. We don't need to know, what region we want to profile, how fine-grained profiling we can do, and so on. We can just capture full fidelity, log it, and analyze it later. Okay, so I will sort of wrap up by talking about FireSim's original purpose, and that was to build a data center scale simulation. So we're not going to do this today, but this gives you a sense of what FireSim is capable of. And of course, if you can simulate a data center, you can simulate a single SoC. So our original goal with FireSim was, again, to say, all right, we have these 1,000-node clusters. We see all of this kind of heterogeneous hardware appearing in data center contexts. How are we going to do this research the way we traditionally do, where we're really going to write RTL, we're going to tape out chips, we're going to build networked systems, and so on? Well, what we would like to do is faithfully model the server systems in our data center, right? And we have to do that at scale, and of course, cycle accurately, or really cycle exactly true to the RTL. But it still needs to be fast enough that we can run real software, because most interesting distributed benchmarks take quite a bit of cycles to run. And of course, we're going to need RTL and abstract software model co-simulation, because we can't fit an entire data center on one FPGA. So there are two main components here, right? We have server simulations. The server simulations tend to be a good fit for the FPGA. That's because we had RTL for building these sorts of SoCs, and we can transform them into server simulations that run on the FPGA. The network simulation, generally speaking, at this level of fidelity, there's little parallelism in things like network switches. And we need something anyway to coordinate many distributed simulations if we start stamping out these server simulations across FPGAs. So we're going to write some code for running a network simulation in C++. And as a side effect, it's also going to manage synchronization between many different server simulations running across many FPGAs. All right, so let's actually build this up from scratch. So we're going to start with a server SoC and RTL. This work was done pre-Chipyard, so server SoC here consisted of a kind of relatively simple quad-core rocket-based system. But of course, this can be replaced with Boom and all sorts of complicated stuff today with Chipyard. But we'll take this sort of for granted as our base server SoC. So it has the parameters you see on the right-hand side here. 4 cores. We're going to model them as if they're running at 3.2 gigahertz, right? Remember, this is a simulator, so we can control what the time, how time progresses. The main thing we added in RTL for this work was a 200 gig Ethernet NIC. So this is a chisel implementation of an Ethernet NIC. It's sitting here in the actual RTL design. So all of this is just RTL. This will take about a quarter of an FPGA on F1. So of course, we don't really just want the RTL. We want an FPGA simulator of one of these server SoCs, right? So we have that same RTL you see here now. It's transformed into this simulator. So again, you can think of it as basically clock gating this thing and adding a bunch of models around it. So you can see that DRAM model appearing here, sitting in between the server SoC and the physical DRAM attached to the FPGA. All of this stuff is sitting on the FPGA fabric. And then there's also PCIe to the host machine on one of these F1 instances. And so this is more like a complete server SoC simulation. You'll see we've tacked on a model of 16 gigs of DDR3. And again, this takes up about a quarter of an FPGA on EC2F1. If you run this with no network simulation, it'll run at like 150 megahertz, plenty fast. And as we'll talk about a little bit later on, having a truly faithful network simulation is going to cost us in performance, but we can still run this at about 40 megahertz with that being the case. All right, so I mentioned repeatedly that this takes about a quarter of an FPGA, and we want to scale out to modeling a whole data center, right? So what we're going to do is drop down 3 more copies of what I just showed you on the previous slide on one of these FPGAs. So now we have this 4 server simulation running on one FPGA. You'll see these little lines going off. These are essentially virtual Ethernet network models that are going over the host PCIe network to the Xeon core. And I'll show you what's happening on the other side on the next slide. But this is basically modeling 4 servers in a data center that can talk to each other over Ethernet, right? And the instance I showed you a few slides ago is not just one FPGA attached to a Xeon host. It's 8 FPGAs attached to a Xeon host. And again, we like to scale out. So we can just drop down 7 more copies of what you saw on this one FPGA. This is running all on one EC2 instance that has 8 FPGAs attached to it for a total of 32 server simulations, right? And now we have that C++ Ethernet switch model I told you about at the very beginning, sitting here running on the Xeon core that's talking to all of these FPGAs. So now each of these simulations will synchronize with this top of rack switch model to get this globally synchronized 32 node sort of cluster scale or rack scale simulation. And even at this rate, we can still run this pretty fast, still 10 megahertz, still 100 to 1,000x faster than a software simulator of a single node. Now, again, we want to keep scaling out. How are we going to do that? Well, because we're running on the cloud, we can now scale out on the cloud. So we can drop down multiple copies of what I just showed you here on 7 more instances, right? So now we have a total of 64 FPGAs, and each of those FPGAs is running this 4 server simulation. And so we get this 256 server simulation of a data center with this 2-level network hierarchy. So what's happening on the network, simulated network here, is we have an aggregation switch model. It's again just a C++ model. It's shipping tokens around that FireSim understands. And this is just running on a regular compute instance on EC2. It's talking over the Ethernet network of EC2 to each of these switch models running on each of these rack scale simulators. And that's how everything is staying globally synchronized across the whole system, right? And so now we have these 256 nodes that can communicate with one another in this simulated world over this 200 gig Ethernet network. And of course, we like to hit a magic number of 1,000 nodes. So we can stamp out 3 more copies of what I just showed you. And 4 times this many nodes gets us to 1,000 servers. Modeled, we've added just another level in the switch hierarchy in our modeled system, right? And again, this root switch is running on a regular compute instance, talking over the EC2 network to each of the aggregation switches in each of these things, which are each talking to a top of rack switch in each of their racks. And so we have this 1,000 node simulator. It's running on 256 FPGAs on EC2F1. And this still runs at 6.6 megahertz, still several orders of magnitude faster than a software simulator of a single node. And so here we can run interesting workloads on here. This is fast enough to boot Linux. Any node in this thing can talk over Ethernet to any other node in this thing. We can customize them, add accelerators, do whatever we want, run distributed stuff on top, all faithfully recreated from the original RTL for one of these nodes. And to sort of sum this up here, we can basically harness millions of dollars of FPGAs that in academia we could never afford to buy. But doing this on the cloud, we can simulate these 1,000 nodes cycle exactly with the cycle accurate network simulation, tying them all together. And if you're running on the cloud, this only costs you $100 an hour to run. So we can run some experiments on this, throw it away as if we never had these 256 FPGAs, which we could never afford in the first place. So this enables us to do things at a scale which we could never do before just because we couldn't get those sorts of resources. And of course, if you can model this, well, modeling one of those quad core systems is no problem. So essentially what this ended up turning into is a tool for doing productive open source FPGA accelerated simulation, right? We didn't sit there and by hand launch every one of those 256 FPGA sims and stitch everything together by hand. There's a ton of automation there. And that automation works just as well. Say if you have 10 benchmarks you want to run on 10 copies of the same simulator. So we open sourced FireSim, it's BSD licensed here. And like I said, it essentially turned into this easy button for fast FPGA accelerated full system simulation. So now you can plug in your own RTL designs or designs you get from something like Chipyard, and you can run these large parallel FPGA builds as well as simulations and scale them to various different use cases. So as you'll learn throughout the rest of this session, all of this complexity is abstracted away from you behind this FireSim command line program. So I showed you this diagram at the very beginning today. That FireSim command line program is going to run on the FireSim manager instance. It's the instance you've been SSHing into all day. And when you run the FireSim command line program, depending on what you ask it to do, it's going to transparently launch build farms and run farms to do all of the heavy lifting. And so if you've used something like Docker or Vagrant, think like that, but FireSim is for FPGA simulators. And the nice thing here is that scripts can also call FireSim to completely automate the process of deploying these simulators. So back in ISCA 2018, before artifact evaluation and all of the conferences, we released with this one script that would reproduce all of the graphs in the paper. For a long time, this was actually sort of the release check for FireSim. When we shipped a new release, we would just rerun this script and reproduce all of the ISCA paper results. And of course, if you can script something like this, you can also run scripts to run all of Spec in 2017. And today, lots of user papers have also gone through artifact evaluation using FireSim. So they've packaged up their artifacts using FireSim, given it to artifact evaluators who maybe have never even heard of FireSim, maybe have never run FireSim, and got them to reproduce the results in their papers. And these are papers both from Berkeley and outside of Berkeley. There's tons of documentation. It's constantly growing. And if you're in academia, you can also get grants for using AWS from AWS. And of course, Xilinx will also donate FPGAs to university researchers. Okay, just to sum up about the community. So I already said this morning, a bunch of people in the community starting to use FireSim, lots of projects with public FireSim support, lots of companies have publicly announced using FireSim, including Sci5, writing a validation paper at VLSI, comparing their shipping silicon versus a FireSim model of that silicon. And then more recently, Galois adapting FireSim for use in the DARPA FET program to basically host other people's security augmented RISC-V designs for attack on the cloud. Okay, lastly, there are a bunch of papers that have used FireSim. This is just a short list of them. There's over 20 more on the FireSim website. You can go to the FireSim website, click publications, and find that whole list. And also a bunch of awards for these users too. And so at this point, FireSim has been used in, this is probably actually an old number now, has probably been used in published work, or has been used in published work from authors at over 20 different academic and industrial institutions. And so this is not just they cited the paper, this is they actually used FireSim to do their experiments. I forgot to fix animation since this morning. All right, so one key feature that FireSim didn't have for a while was the ability to run on local FPGAs. So we actually kind of started backwards. We started with cloud FPGAs and now we're moving local for certain use cases. So all of that automation we added to make it very easy to run stuff on cloud FPGAs now extends to on-prem FPGA support. And so at a recent deadline for presentation we had to give at a research retreat, we went from basically a machine that was parts sitting on the ground to a complete machine running simulations in about an hour and 40 minutes. And so all of this is documented on the FireSim website. It's very easy to build sort of the same standardized host platform and get started very quickly. And you can use all of these existing FireSim features both at scale and locally. So it's very easy to get started locally. And then when you have a deadline, flip one switch in the FireSim configuration files and move to running on hundreds of FPGAs in the cloud. If, for example, you just have a design, you want to stamp out many copies and run lots of benchmarks in parallel. And you'll hear about this all throughout the day today. So with that, I'll wrap up this intro talk, hand it off to Abe. But are there any questions in the meantime?